Let's verify whether the given set here G, a unit set containing 0, is a group under the usual addition. In order for us to verify whether this set is a group or not, this should satisfy all conditions. Aside from G sub 1 or G1, G2, G3, we also need to establish that this set is non-empty and at the same time closed under the operation. Of course, this is clearly non-empty. Okay, that's very clear that it's non-empty since it contains an element which is 0. It's a unit set. The next thing here is we need to establish that it is closed under the usual addition. Since we only have one element, and under addition, if we're going to add 0 for another element which is actually just itself, we have here 0. Hence, we have this Cayley's table here on this side, and we can have here the result for the usual addition being 0. Since 0 is element of set G, then we can say that this is actually closed and the closure property holds. Now with this 2 in mind, we can proceed to our 3 conditions, G1, G2, and G3. If one of those 3 conditions will not be met, then definitely this set G containing 0, a set containing 0 is not a group under usual addition. For G1, we just need to establish that star is associative in set G. Since there's only one element, we can also try to establish, say for example, let A, B, and C element of G. But of course, we all know that all of them are 0 because we only have one element. It's just that we just need to show that this is true, even if it's obvious, so that it could be part of our practice as well. So if we have here 0, okay, usual addition, that's what it meant. So we have here 0 plus 0 plus 0. On the other side, 0 plus the group of 0 and 0. Both sides will contain 0, and hence we can establish here that the operation, the usual addition, I forgot to mention here, let star be usual addition, so that we can use the symbol star as we go through, and we also have the symbol star here. So nevertheless, G1 star is associative in G. Therefore, G1 is satisfied. Let's proceed to G2. G2 means there should be a presence of an identity element. The identity is any element that when subjected with another element using the operation defined, we will have the element itself as the result. So let's try again. It's very obvious here, but just for practice, let's have here, let A be element of G. We need to find E. This is also element of G. Let me rewrite it. Element of G such that we have here A star E equal to E star A equal to A. Okay? So this is true now for all A element of G, though we only have one element here. Of course, our A here, using usual addition, that's usual addition. A plus E. This other side we have E plus A. Okay? And then we can now equate both of them because, of course, let me use other color here. Of course, we know that E plus A can be written as A plus E as well. So we have the two, you have the same expressions now. So if we have A plus E is equal to A, as indicated here, and then we can subtract A both sides, we will have here an expression E is equal to 0. This is the identity element of this set. And of course, this is the only element of G. Therefore, we say that G2 is satisfied. Okay. If we could come up with other identity element aside from 0, then it's not part of the given set, then definitely G2 is not satisfied. Let's proceed to the last condition for group G3. Okay? For G3, we let A element of G, and we need to find the inverse of A, which is also element of G, such that A star A inverse is equal to A inverse star A equal to E, which is 0. If we could identify the element A inverse for all element of A, for all A element of G, then if it's 0, then we can say that G3 is satisfied because we show that E is also an element of, or A sub, the inverse of A is also an element of G. So, of course, using usual addition, this is A plus A inverse. The other one, A inverse plus A, which also be written as A plus A inverse. So, we have the same expression now. This time, we can now have A plus A inverse is equal to E, which is 0. So, if A plus A inverse is equal to 0, we can cut that one. Therefore, we have here A is equal to negative of A. But of course, we only have one element in our set because our set G is a set containing 0 itself. That would mean if A is 0, our A inverse is also negative 0, which is just 0 itself. And this is element of G. This means that G3 is satisfied. With all of these three conditions met, we have G3, the existence of an inverse, G2, the existence of identity, which are both 0, and we have established here that star is associative in G. We can now say that G is grouped under star, which is we defined as the usual addition. G, which is a set containing 0, is a group. So let me rephrase this one here. So G, which is equal to the set containing 0, is a group under star, which is the usual addition. So we have shown here that this set is a group under usual addition. Thank you very much for watching.